In this video, we're going to explain how change of coordinates works with an actual function and an actual somewhat complicated change of coordinates. So we're going to be using polar coordinates, which you're probably quite familiar with, but we're going to go through it step by step to actually show how the methods of using pullbacks work and sort of make everything very clean and nice. Okay, so what we're trying to do is we want to find the volume of the solid region below the paraboloid z equals 3 minus x squared minus y squared and above the xy plane. So you can draw this if you take the circle of radius 3, root 3, and then take the point 3, 0, 0, 3, sort of draw the paraboloid above it. So it'll look something like that. This is the circle of radius root 3 in the xy plane. Okay, so what we want to do is we want our function f of x, y to be z, so that'll be 3 minus x squared minus y squared, and our region should be the disk, so it should be x squared plus y squared is less than or equal to root 3. Okay, so if we wanted to compute this using our methods using Cartesian coordinates, we would be integrating over the region R, f dx wedge dy, which is the same thing as the double integral. Okay, so this is a little bit complicated, but I won't write down the region first. I'll say the double integral over the region R of 3 minus x squared minus y squared dx dy, and then I need to write the x bounds first. So the second bounds will be the y bounds. So, as you probably remember from multivariable calculus, this is something that's much easier done in polar coordinates than in Cartesian coordinates. Although this one I don't think is too terrible. Well, it might be pretty unpleasant. You'll have to do some substitution. So I don't want to do that. So let's change our coordinates. So this region is pretty nice in polar coordinates. It's just the rectangle where theta goes from 0 to 2 pi and r goes from 0 to root 3. And so what I want to do is rewrite in polar coordinates. So what exactly does that mean? So I want phi to send the xy region, so it's this disk in the xy plane, to a simple region in polar coordinates. So in r and theta coordinates, I should have, oh well, this is totally out of scale. Something like this. So root 3, which is approximately 1.7, and then 2 pi. So this is also super out of scale, but maybe it makes a little more sense. So I want phi to do that because I want to be integrating over this region. This region is easy to integrate over. For some reason, Fortney really likes to think about theta as the first coordinate in polar coordinates and r as the second. I'll show you why. Well, I'll explain just right now why I don't like doing that. So basically, what happens if I think about r theta coordinates, if I think about what kind of rectangles are considered positive in r theta coordinates, if I have, let's take that little arrow that starts at that little point. So maybe, where is that? It's a little arrow. The point's right there, just increasing r, not increasing theta, so it should go out that way. And then now I take a little arrow at the same point, increasing theta, but not r, so it should point that way. So these little arrows, this is basically like d by dr, and this little arrow kind of represents d by d theta. And if I plug in, into dr wedge d theta, d by dr, I mean, obviously, like that, okay, obviously that will be positive. But basically, if I take this little rectangle and I think about, what the rectangle spanned by these two vectors, and I take it into the xy plane, it's sort of oriented in the same way, right? So if I go, actually these the squiggles maybe aren't the best thing to draw. What I should draw is the arrow going from red to pink. So when I draw the arrow going from red to pink, it still stays counterclockwise. And so this sort of is behind the reason why I like to think of dr wedge d theta as sort of my volume form, or at least is proportional, or is my volume form in r theta coordinates. I mean, it doesn't have to be, but that's the convention that I personally like to use. So when I say I mean literally me, myself, and a lot of other mathematicians as well. And then so if I go back into my Cartesian coordinates, and I want to draw at the same point a positively oriented rectangle, like where if dx wedge dy eats it, I get a positive number. I take some rectangle like this, dx wedge dy eating that, I should be putting in the purple vector first and then the green vector. So if I look, this is also counterclockwise. So the whole point of this is, if I consider my volume form in r theta coordinates to be dr wedge d theta, I preserve sort of the correct orientation of the areas. If I want to, and this is borne out by the fact that if I take, so I'm going to define phi in a moment, but if I take phi pullback of phi, or inverse pullback, or it'll be if I take phi inverse pullback of dx wedge dy or phi pullback of dr wedge d theta, I get a positive multiple of the other. So I really want to define my dr wedge d theta as sort of considering that to be my positive area. And this matters, right? Because if I change the order in just a regular integral, I don't get a change in sign, but we are considering changes in sign. Okay, so for all of end rant. So all that being said, I want phi to go from xy to r theta, and I want x to be r cosine theta, y to be r sine theta. But that really is going the wrong way, right? This should define phi inverse. Phi is defined some other way. And you can define it using r equals square root of x squared plus y squared, and phi equals some branch of the inverse tangent. But we don't actually even need to do that because it doesn't really matter what phi is. So what I'm going to say is that phi inverse, let me not box that actually. So what this means is that phi inverse of r theta is equal to r cosine theta, r sine theta. And it doesn't really matter what phi is, because I know that phi is going to send the disk of radius root 3 to this rectangle, and that's all I really need to know about phi. So that defines phi inverse. And I need to figure out, so I know I want to compute this integral. I just need to figure out what the new, oops, don't want to do that. I want to figure out what the new integrand is in the new region. Okay, so I need to take phi of this region. So that is going to be the region from in the r theta plane, where r goes from 0 to root 3 and theta goes from 0 to 2 pi. So this is equal to phi of the disk of radius root 3 in the xy plane. And now I want to take this composed with phi inverse, right? So I need to put f composed with phi inverse, and then I want phi inverse pullback of dx wedge dy. And this makes sense because phi inverse goes from polar to Cartesian. So phi inverse pullback will take a form in xy coordinates and put it into r theta coordinates. Okay, so let's compute first let's compute, let me do this in a different color. Let's compute this part. So f composed with phi inverse is equal to 3 minus r cosine theta squared minus r sine theta squared, which is 3 minus r cosine squared theta minus r squared sine squared theta. Sine and cosine add to 1, so this is just 3 minus r squared. And now let's figure out this part. So I want to take phi inverse pullback of dx and wedge it with phi inverse pullback of dy. And these are both easy to compute. Remember phi, so d phi inverse is cosine theta, sine theta, negative r sine theta, r cosine theta. Put an extra c there. And so I know that phi inverse pullback dx is equal to, well, is determined by d phi inverse transpose times 1, 0, which is the first column of d phi inverse transpose, which is going to be cosine theta dr plus minus r sine theta d theta. And similarly, phi inverse pullback of dy is equal to d phi inverse transpose times 1, 0, 0, 1. And then I take the first coordinate and it's the coefficient of dr, second coordinate's coefficient of d theta. So what I end up getting is sine theta dr plus r cosine theta d theta. Remember, there's another way I could have done this. I could also have computed phi inverse. So alternately, phi inverse pullback of dx wedge dy is completely determined by what it does to d by dx, the pair d by dx, d by dy. And what I can just do now is dx wedge dy applied to d phi inverse d by dx, d phi inverse d by dy, and then this is just the first column of d by d phi inverse, so cosine theta d by dr. Sorry, this should be d by dr and d by d theta. What am I doing? Okay, so d by dr, d by d theta, d by dr, d by d theta. So this will be cosine theta d by dx plus sine theta d by dy minus r sine theta d by dx plus r cosine theta d by dy. And then this will just be cosine theta times r cosine theta minus sine theta times negative r sine theta, which will be r. So here, oh right, so this is going to be r. This is the coefficient in front of dr wedge d theta. So this tells me that phi inverse pullback of dx wedge dy is r dr wedge d theta. And I realize now that I forgot to take the wedge product of these two things. So instead, what I could have done is taken the wedge product of cosine theta dr minus sine theta minus r sine theta d theta wedge sine theta dr plus r cosine theta d theta. And this wedge product, so the dr will be the same thing, r cosine squared theta plus r sine squared theta dr wedge d theta. So it's the same thing. I end up getting r times dr wedge d theta. So when I compute what this integral actually is, it's going to be the integral over this rectangle of 3 minus r squared times r dr wedge d theta, because I'm putting together all of the pieces. And then now this is something that's pretty easy, so I can just rewrite this. So I need to go from 0 to 2 pi in theta, 0 to root 3 in r, and then this will be 3r minus r cubed dr d theta, which is now something I can just compute because I know how to integrate polynomials.